Good evening. Hi guys. Thanks for coming along. It's turning out to be a bit of fun for the evening. Yeah. So, first of all, tonight, last month's talk was on infant stars and star formation, and someone asked a really interesting question. Do brown dwarfs, do you see bipolar jets? I don't know who asked the question. Was anyone who was here? But it was a really interesting question. I think I said, look, I'm unsure and I'll find out. So the bottom answer is yes, brown dwarfs form protoplanetary disks, exoplanets and bipolar jets. Quite a surprise because usually the jet's associated with sort of higher energy events, but obviously there's enough energy there, you know, with twisted magnetic fields to be pushing out charged particles. And here is an image even here of a brown dwarf, and you can see big jets, her big Haro objects we talked about. That's almost a light year across. Amazing. That there's also an exoplanet. That's an image of an exoplanet, 5 Jupiter masses in orbit around a 25 Jupiter mass brown dwarf. So that's just I thought it's just a couple of minutes, just following up on that interesting question from last month. Now, tonight's feature is about the solar system. It's going to focus on the solar system with an aim of changing the way you think about the solar system. Remember this, I don't know about you guys, but I went to school in the 1970s and I was told the solar system went something like, well, in the middle there's the sun, it's a star. There wasn't too much more information than that given. There were 9 planets, all in a straight line, the sort of plane, not much more information given than that. There were different sizes. We weren't taught about any particular pattern to the sizes or any trend going on there or the reasons behind that. We were taught that there was a belt of rubble between Mars and Jupiter. No real explanation of what that was all about. And we were told there's sort of comets zipped across the solar system from time to time. Weren't too sure where they came from, probably from some yet unknown regions of the solar system. So that's what I was taught. And the main sort of thrust of tonight is that modern astronomy has changed our view of the solar system. How we now have new generations of telescopes, like the Keck there on the left. It's got a 10-metre primary mirror. It's got adaptive optics. It's got CCD, very sensitive sensors that can look into the near infrared. You've got large radio and millimetre, sub-millimetre arrays, like here an image in the Atacama Desert of the ALMA, the Atacama Large Millimetre, Sub-Millimetre Array. We've now got wonderful space telescopes such as Hubble there. New Horizons craft that's flown out into the Kuiper Belt is photographed close up of Pluto. We've now got supercomputers that crunch numbers and large numbers to create models and so on. So the whole area of astronomy has changed so much such that our view now of the solar system has changed. And that's why tonight's talk is titled A Modern Perspective of the Solar System. What's there and why is it there? So tonight we're going to address the solar system, what's there through modern eyes with our new technology. Address the problem that keeps coming up time and time again. Pluto, is it a planet or a dwarf planet? We're going to put that one to rest. And how did the solar system form into exactly what we see today? So when I went to school, they didn't know really. So I've put it into 2 parts here. Part 1 is what's there, and then part 2 is why things are there. Can you see past me, Brenton? All good? Yep, so part 1, what's there? So I've split this into 4 main groups. We'll talk about the sun, then we're going to talk about the planets, we'll talk about the small bodies, and then we'll talk about the comets. So the sun. Yeah, I was just told at school it was just a blob called a star. So we now know it is a star, which means, now I understand now, it means it's just a big round ball of hot gas known as plasma. It's a spectral class G2, which means it has a surface temperature of about 5,800 degrees. It's on the main sequence dwarf, which means at its core, it's burning hydrogen into helium. Check this out. The sun burns 600 million metric tons per second of hydrogen into helium. Check that out. The sun's life expectancy is thought to be somewhere between 10 and 12 billion years. We know now from meteorites and stellar models it's about 4.6 billion years old, so it's roughly about halfway through. And the question I had to myself is, with the unaided eye, without a telescope, how far away could you see the sun in the night sky if you were in some hypothetical planet or somewhere? It's visible for about 50 light years. So, putting the sun in perspective there, it's over 99.86% of the mass of the solar system is the sun. It's all about the sun. And I've just brought a little prop here. Oh, I'm going to set this thing off, aren't I? If this was Earth, it had to happen. If this P was Earth, this frozen pea, this on a scale would be the sun. Check that out, huh?
Half the peas on the side.
Bit of pea there. Hey, I'll leave it there. There you go. Look at that. So that actually is the scale. The diameter of the sun is 110 times the diameter of Earth's. And you'd fit 1.3 million Earths fit inside the sun, volume-wise. Whoa, check that out. So it's just a bit of interesting figures there.
How far apart would they be to scale Earth and Sun?
150 million kilometres. I couldn't, from here, I couldn't tell you.
It's about 70 metres, isn't it?
Is it about 70 metres? Okay.
So use the same model.
Right, okay, yeah, use over there, yeah.
And I visualise that if the Swiss ball's on the middle of a rugby field on the halfway line,
Yes.
you're 10 metres behind the touching goal. So you're in the crowd behind the goalpost,
Yes.
holding a pea. That's the Earth.
So if that was the Earth in the middle of the field?
Or the sun in the middle.
Sorry, the sun in the middle,
halfway line,
at the halfway line.
you're the pea, 10
Right.
metres behind the end goal line.
Wow, yeah.
The try line's 15 metres,
Yeah,
touching goal
yeah.
60.
That's good that you worked it out. Yeah.
It's a long walk around Eden Park. Doing
So it's just-
108,000 kilometres an hour.
So it's incredible. So one of the key messages from here, it's all about the sun. Just that gentle, he should be okay there. Yeah. Okay, so that there is the sun. So let's have a look at the planets. There they are there. And I need a bit of help. This is for the kids in particular. I need a little bit of help, guys. I keep forgetting the names of my planets, what order they are. So, first what planet is this? Mercury. Yes, indeed. It's Mercury. Yeah. So Mercury is about a third of the size. We're going to do a bit of a tour. We're going to do a bit of a tour here of the solar system, of the planets, and then we'll bring it together in a nice sort of theme. So Mercury is about a third of the size of the Earth, very rocky and dense. Its iron core extends out to about 85% of its radius, compared with Earth's, sort of roughly about 50%. So it's got a very high iron content. It has no atmosphere to speak of. It's heavily cratered because of that. There's nothing to stop the impacts. And it's very, very close to the sun, so it's got a very high temperature. The temperature highs get up to about 430 degrees. I'll put that in Celsius because we can relate to that day to day. So let's put Mercury there. What's the next planet, guys?
Not the moon.
What's the next planet? Venus. Venus, yeah, good. Venus, yeah, absolutely. This here is Venus, this next one. It's about the size of the Earth. They sometimes call it Earth's sister planet because of its size. That's where the similarity ends. It is also rocky and dense. It's got a relatively young surface because a lot of volcanic activities, a lot of lava's flowed over it. Its surface is somewhere between 300 and 600 million years old, so that's a relatively young surface. It's got a very thick atmosphere that's predominantly carbon dioxide, very thick, dense, opaque clouds, where images of the surface of it from orbiters is done with radar. Pressure, an atmospheric pressure of 93 bar. That means we live at sea level on Earth at 1 bar. That's sort of the unit. So the pressure on the surface, the atmospheric pressure is 93 times that on Earth. Needless to say, you wouldn't hang around to complain too much about it. You'd be crushed. This is the hottest place in the solar system, apart from the surface of the sun, obviously, but in terms of the planets. Temperatures get up to 460 degrees Celsius. Hotter than Mercury because of the carbon dioxide thick atmosphere, the greenhouse effect. So just put here, there's a little bonus in here, so you can say, oh, I've seen pictures of the surface of Venus. The Russians sent a series of craft called Venera and Venera 13. Most probes and crafts only operate for 1 to 2 hours before the conditions, the high temperatures and the atmospheric pressure slowly degrades it, and they lose contact with it. So Venera 13, one of those pictures is from the front, one of them's from the back of the craft, just looking down at the surface around it. So yeah, there you go, that's a little treat. Come in, yeah. So let's put Venus there, shall we? Next to Mercury. What's the next planet, guys?
Earth.
Earth, yeah. Home to 400 million cats. Oh, and I forgot the 8 billion humans as well. They're the most destructive species on the planet, let's say. Who said that? So Earth, you're mostly familiar with it, but once again, it's rocky and it's dense. Its atmosphere is mostly nitrogen, 78%, oxygen, 21%, and there's a sort of less than 1% of argon and carbon dioxide and a few others there. They were my 3 cats at home, by the way. And there's Earth. Let's put Earth there, shall we? Next to Mercury and Venus. They're all small, rocky and dense planets. Okay, guys, next planet.
Mars?
Yes, Mars, yes. Mars needs guitars, absolutely. There's Mars. So Mars is half the size of the Earth. This gravity on the surface is about 1/3. So if you're in your spacesuit bouncing around, the moon's about 1/6 the gravity of Earth. You're about 1/3 on Mars. Once again, it's very rocky and dense. Very, very thin atmosphere. The atmosphere pressure on Mars is less than 1% than it is on Earth. Very, very thin atmosphere. It's mainly carbon dioxide. The average temperature on Mars is minus 60 degrees. As I've often said, almost as cold as a student flat in Dunedin in the winter. Here's your little treat for Mars. I love that picture. That's in Gale Crater, and it's the track marks a few days prior of the Curiosity rover. I just love that. It's just so wonderful. You know, we can't help ourselves. We've got to leave our mark on the planet. So I just love that picture. So let's put Mars there. Move on. What's this planet, guys? The next one.
Jupiter.
Jupiter, yeah, Jupiter. So Jupiter's a very large planet. It's diameter-wise, it's 11 times the size of Earth. It's a large, what they call a gas giant, predominantly gas. And I can't emphasise this enough because it's going to come up time and time again. It's predominantly hydrogen and helium are the 2 gases that make up almost all of Jupiter. Very thin atmosphere. It doesn't have a hard surface, but it blends into when it sort of solidifies, but there's no definite surface you could walk on. It has a very thin atmosphere, once again, hydrogen and helium. Can't emphasise that enough. It's got this big red spot here that you can see. That's a 400-year-old storm in the atmosphere. And that is 1.3 times the size of Earth. You might think, trying to visualise that. Here's your little treat for Jupiter. That there is puts it in perspective of Earth next to the red spot, which is just a big 400-year-old storm. Almost as long as we had to wait for the alarms to settle down tonight. So let's put Jupiter there, shall we? That's not to scale, but I'm just making a point here. Look at the suddenly change in what's going on here. What's the next planet? Yeah. Saturn, yeah, Saturn with the big prominent rings and stuff. Absolutely, Saturn. So that's a Very large gas giant as well, about 10 times the size of Earth, so not quite as large as Jupiter, but still very, very large, predominantly hydrogen and helium gas. I just can't emphasize that enough. Hydrogen and helium. One, like Jupiter, a very, very low density, and of course it's got its famous ring system. Its density is the lowest density in the solar system. It's less than the density of water. So if you had a bath big enough, Saturn would float on it. Warning, upcoming dad joke, and if you pull the plug out, it leaves behind a ring. Sorry, bad dad joke. But it would float on water. Its density is less than that of water. So let's put it there. Let's just sit it beside those other ones, and hopefully you're starting to see the picture forming now. What's the next planet?
Pluto.
Oh, you're right, yeah, Uranus, that's right, yeah, you're right. That's Uranus, yeah. So Uranus is about 4 times the size of Earth. It's what they call a large ice giant. So it's made up of gas and ice. And the ices in particular is water ice, methane ice, and ammonia ice. You can just see up here we go. This thing's a little bit funny. So here's the formulas for them up here. No, it won't work. Oh, there it goes. It's got a very thin atmosphere, predominantly hydrogen and helium, and it's got some methane in there as well. So I'll put it there. Okay, next planet. Neptune, yeah, big blue Neptune there. So that's Neptune. So Neptune is 4 times the size of Earth, so it's comparable with Uranus, but once again, very, very large compared with the Earth. It also is a large ice giant, so it's got gas and ice going on. Once again, your ices here is your water ice, your methane ice, and your ammonia ice, with a very thin atmosphere of hydrogen, helium, and methane. Why are those two blue? It's the methane. Methane tends to absorb red light and infrared light and is able to scatter and reflect off your blue light, so it always appears blue. The methane's a little bit thicker in Uranus, so it's more hazy, so there's slightly less blue hue, in case you're wondering. Why the blue and why are the different tones? That's why. And there you go. So what's the pattern there, guys? What pattern can you see there? You got 2 groups, haven't you? Look, small, 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 large, 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 large. It really splits it up. 2 main distinct groups of planets that make up the solar system, and each group is together. So you've got these 4 inner, what are called terrestrial planets, which is Mercury, Venus, Earth, Mars, which are close to the Sun. They are relatively small, they are relatively dense, and they have solid surfaces. They are dominated by metals like your iron and your nickel. It tends to go towards the cores. And silicates, which is silicon and oxygen combination of minerals that go towards to make up rocks. Then you've got your 4 outer gas and ice giants, which is Jupiter, Saturn, Uranus, Neptune, and they are further out from the Sun. They are large, they have metal, rocky cores. That's something you'll see later on, I haven't mentioned it just now. Relatively low density, ill-defined surfaces, and they're dominated by hydrogen and helium gases. I can't emphasize that enough. And they do have those, Uranus and Neptune have got the water, the methane, and the ammonia ices. So those are your 2 groups that are going on. And you see the pattern too. You might be thinking, why are there 2 groups? And why are all the small rocky ones in the inner part of the solar system and the gas and the ice giants in the outer part of the solar system? That's the sort of questions that you're going to be asking yourself. We call it a dichotomy of planets, division, 2 groups. And why are they all in the same orbital plane? Could never work that one out at school too. The teacher could never tell me why. So both those observations of the planets are explained by how the solar system formed, which we will do in part 2. Then every class has got a problem child, and the planets are no different. And then there were 9. So life was good. There was 8 planets. And then this guy, Clyde Tombaugh, at the Lowell Observatory in Arizona in 1930, he was looking at some photographic plates, looking for another planet out there. And here's his photographic plates just 6 days apart in January 1930. And he noticed this spot here. All the rest of these spots were all stars. But he thought, look at that one and look at this plate. 6 days later, that's moved. That's that same spot. It's moved. And that was evidence that there was another planet further out in the solar system. And that's how Pluto was discovered. And so everyone decided, right, we've got 9 planets. And then Pluto in 2006 was demoted to a dwarf planet. Gosh, what a fiasco that was. Everyone was up in arms about it and so on. What's going on here? So what happened? What happened there? Well, it all came down to, up till the 1990s, we all knew there was 9 planets, and every school child learnt the names of all 9 planets, and life was pretty good. Along came this next generation of telescopes with their big 10-metre primary mirrors, their sensitive CCD images. They could even start looking into the near infrared with these sensors. And they suddenly realised that there's a hypothesised area up there called Kuiper Belt that thousands of other rocky objects were thought to be, and they discovered it. They realised that Pluto shared its space with thousands and thousands of other rocky objects of comparable size. And suddenly they realised you can't give the kids the name of 20,000 planets to go home and learn. Might be a bit of a problem there. So they realised we've got a naming problem here. We've got to sort something out. In fact, some of these objects here, like these 5 here, were quite also large and round, and some of them were actually bigger than Pluto. So they realised Pluto, there was nothing special about Pluto. Even its orbit wasn't right. You can see here, look, its orbit is tilted at an angle too, as opposed to the rest of the planets here. Here's the sun down here, and all the planets in a nice single plane. So there was a problem. So they realised we've got to sit down. The International Astronomical Unions realised they've got to sit down and work out some criteria for what's a planet and what's not a planet. So they came to 3 criteria for something to be called a major planet. One is, does it orbit the sun? You might think that's a damn obvious thing to ask, isn't it? Well, it separates things from moon. So, for example, here, the Earth goes around the sun. So, yeah, that's a planet, major planet. But the moon doesn't. It goes around the Earth. So that's obviously not a planet. So that was a first criteria. Second criteria is, does it have enough mass to allow gravity to shape it round? Because if something hasn't got enough mass, it hasn't got strong enough gravity to make it a nice round colour. And you can see Earth there is nice and round because it's got enough mass for gravity to mould it into a round shape, which we take for granted. But look at that asteroid on the other side. It doesn't have enough mass to mould it into something round, where gravity is trumped by the electrostatic forces holding it together. And it looks more like a potato, doesn't it? So they thought that's one way to decide how large something is, how to define how large something is to determine whether it should be a planet or not. Is it round? So Earth obviously fitted in with that criteria. Pluto fitted in with that criteria too. Pluto is round. You need something to be very roughly about a diameter of about 500 kilometres, very roughly, to be round. The other one was, has it cleared the neighbourhood? Has it dominated the orbit, its sort of orbit area around the sun? Has it got any other objects of comparable size? And once again, the first 8 planets, yeah, they dominate their orbits. There's a little bit of rubble and stuff in there, but nothing of any significance. But Pluto, as you're just seeing, has got thousands of objects in its vicinity, and some of them very comparable sizes, some of them larger than Pluto. So I realised, they thought, aha, this is a good criteria. This is our third criteria, and this is where Pluto fell over. So, out of these 3 body definitions, does it orbit the sun? Does it have enough mass to allow gravity to shape it round? Has it cleared the neighbourhood? That enabled the Astronomy Union to come up with some definitions. And they sort of look, it's called major planets that meet all 3 criteria, and those are the 8 planets we discussed first. Dwarf planets meet the first 2 criteria, that it orbits the sun and it's large enough to be round. Now, Pluto fitted in here, but that does not meet the 3rd criteria. Pluto obviously slipped down from being a planet to a dwarf planet, so the Plutonians were pretty upset. But it wasn't all bad news. The asteroid Ceres in the asteroid belt was actually large enough to be round, so that got promoted. So the Caesareans were pretty happy with that one. They got promoted. So that got promoted, so it all wasn't bad news. And then the others they called minor planets, like those your asteroids. KBOs, that's Kuiper-Belt objects. Those are all the other little rocky things that share the same space with Pluto. That's a decent size, by the way. It's a sort of a, which we'll talk about shortly. It's a torus or a donut shape. That's quite some size, which we'll talk about. And OCOs, that's Oort cloud objects, also known as small bodies of the solar system, but they're called minor planets. And then out on their own, comets, because they're the nomads. They don't live anywhere in particular, comets. They're zipping through the solar system. So they decided they would call them their fourth category. So that's how it all came about, and that's now how they classify objects in the solar system. So that's the sun, the planets, and the definition of a planet. Let's talk about these small bodies now. And as we mentioned, there's we talked about the Kuiper Belt. We're moving in a little bit further here, and there's two main groups. The first group are rocky objects known as asteroids, and here they are here, that's the name up here. Rocky objects known as asteroids, and there's two main regions where they hang out. The first is this belt you can see here of rubble between the orbits of Mars and Jupiter. And there's many thousands of them in throughout that rubble. But there's another little region too, and that's these Lagrange points of L4 and L5. In Jupiter's orbit around the Sun, 60 degrees behind Jupiter and 60 degrees in front, there's these areas called Lagrange points, which are gravitationally stable points, where if you get objects there, they'll sit there quite happily with minimal disruption. And you probably heard, oh, where have I heard Lagrange before? The James Webb Space Telescope at Lagrange point L2, and that's just in another, there's 5 Lagrange points, so I won't go into that right now. But there's L4 and L5 are 60 degrees ahead and 60 degrees behind an orbit of, say, a planet, in this case Jupiter. And there's quite a few thousand asteroids, small rocky objects, sitting in those two locations as well. So that's sort of two there, all in one region. And then there's the Kuiper Belt and the Oort objects, or the Oort cloud rather. And here's your Kuiper Belt. And it's, as I mentioned, it's like a donut shaped or a torus, big area here. And that extends from 30 to 50 astronomical units. An astronomical unit is the distance from the Earth to the Sun, which is 150 million kilometres. And it's just a nice unit to talk about how far away planets are. To give you an idea, is Mars is roughly, I think it's about 1.5 astronomical units away. Jupiter's from the Sun. Jupiter is 5 astronomical units from the Sun. Saturn is 10. Uranus, I think it's 20, and then you go up to 30 to Neptune. So Neptune's a long way out, as you're probably aware when you read about it, so on. So 30 to 50. So these objects are small and they're a long way out. So that extends 20 astronomical units, that area. So you can see why it took a long time before they actually discovered it. Then there's another region, which we're going out a light year this time. So obviously this is not to scale, and this is instead of like a donut sort of ring around, if you will, and sort of in the plane with the planets. This is a sphere of objects, icy, rocky objects called the Oort cloud. The Oort cloud still has been discovered. It's hypothesized to be there, and we'll talk about that shortly with comets, but there's a lot of evidence that it is there. So the Kuiper Belt and the Oort cloud are the home to rock and icy small objects of the solar system, known as Kuiper Belt objects and Oort cloud objects. So that's a whole light year out. That's huge. To give you an idea, put that in perspective, what I should do, I've been talking in astronomical units, 55,000 astronomical units. There I was trying to sell you the concept that 30 to 50 astronomical units was a long distance. You're talking 55,000 out here. That's a light year. A light year is the distance that light travels in a year. Light travels at 300,000 kilometres per second, and in 1 year it travels 10 million kilometres. That's 1 light year, and that's how far out that is. Hypothesised to be there. We'll talk more about it shortly, and we'll talk about how it got to be there too. So now let's move on and let's talk about comets. So comets are these rocky, icy objects that zip through in the inner solar system and look pretty cool. And they are, no surprise, they come from the Kuiper belt and the Oort cloud. They have highly elliptical orbits, so instead of being the round orbits of a planet, they swoop in at sweep angles through the inner solar system, come around the sun and head back out to the outer solar system. There's two groups of comets called short-term and long-term. Short-term comets are those, their period, in other words, from, that was the sun, and you're going yay like that in around the sun and back out again. They do a complete loop, and that's what you call your period. So short period is considered, if you can do that inside 200 years, you're a short period comet. And they are thought to originate from this Kuiper belt here. This won't quite do. Here it is here. Here's your Kuiper belt. And that is the origin of those short period comets. Long period comet refers to comets that take more than 200 years to do a complete circuit around the sun or solar system. And they are thought to originate here from this Oort cloud a whole light year out. It's hypothesized they're out from there. And we'll talk about what makes them head out there shortly. So those are comets, and they're very nomadic. They don't really have a home. They come from the Kuiper belt and they come from the Oort cloud, but they're out on their own once they've left those regions because they're just nomadic travelling throughout the solar system. So just wrapping up the solar system, what's there in a summary. So you've got your centre there, you've got the sun. It's all about the sun. The sun is 99.86% the mass of the entire solar system. You've got your 4 inner planets there, which are all small, rocky, dense. You've got your 4 outer planets, which are a lot larger, and they're very low density of ice and gas. You've got your strip of hard, rocky, small objects in the asteroid belt and the Trojans, either side of Jupiter. Then you've got your Kuiper belt out here of rocky, icy objects just outside the orbit of the planets. And then way, way outside here, you've got your Oort cloud about a whole light year out. You've got your short period comets down here, and you've got your long period comets as well. So that's summary of the solar system, what's there. Let's talk about why those things are there, why they are as they are. So let's talk about the sun first up. Why is it all about the sun? Why is the sun in the middle? Why is the sun so large? Why does it just dominate everything in the entire solar system? The bottom line is because it's all about the formation of the sun. Stars form when you get these huge, big, large, what they call giant molecular clouds. These big regions of space, they're multiple light years across. They're very giant. They call them giant molecular clouds. Giant because they are huge. As I mentioned, they're sort of light years across. They're very cold. Average temperature in there is about 10,000 degrees Kelvin, which is minus 263 degrees Celsius. So they're very, very cold. They're very dense regions, relatively dense. The region around the sun is about 1 particle per cubic centimetre in this sort of neighbourhood of the sun. These regions here have anywhere between 100 and 1,000 particles per cubic centimetre. So they're relatively dense, they're relatively cold, and they sit there, they glow in the infrared. I just really wanted to show you this here. So here's the constellation Orion, as you can see here, and there's the Great Orion Nebula here as well. I'm going to just, oh no, it's all over there, it's got the other pointer. So you can see that little pink area in the picture on the left, that's the Great Orion Nebula, and we all look at that with our telescopes and go, ooh, isn't that wonderful? Oh, I've seen the Orion Nebula star-forming region, and you think, oh, that must be the Orion gas cloud, giant molecular cloud. No, it's not, because you suddenly look at it, the same area in infrared over here, and look what you can see. Just that whole region is a big giant molecular cloud where stars are going to form. And what happens is something will set that in motion. We talked about this more last month, but something that this cloud's reasonably stable there, magnetic fields and a bit of gas pressure is keeping it stable, and it might be another cloud passing by, a supernova explosion or a pressure density wave and a spiral galaxy coming up behind it. But the bottom line, something will trigger it, start collapsing down and starting to rotate. and you get little clumps, areas, regions in there that are a little bit more dense than other regions, and they form into clumps, and those areas start just collapsing in onto themselves. Each one of those will form into a star, and that's how our sun would have formed. So you get these big clumps, and that's pretty much how it all happens, starts to happen. These clumps form down, forms a star, and that's what it's all about. The solar system is just, the rest of the solar system, just a consequence of star formation. So the planets, why are they all in the same orbital plane, all in a relatively straight line? The bottom line is, as you're getting all this gas and dust in this clump, that's shrinking down, down, down with the force of gravity, but it's also spinning faster and faster and faster. And what happens when things spin faster and faster? They get hotter and hotter, but also as they shrink, it gets faster. Why? It's conservation of angular momentum. You probably see the ice skating lady with her arms out spinning sort of, around yay fast. She pulls her arms in. You notice that next time on the TV you see it. She starts spinning so much quicker because she's brings her body in, so she starts speeding quicker and quicker. So as that cloud starts contracting down, it starts spinning faster and faster. It's getting hotter and hotter. And there's two reasons why, but you start getting a disk forming in the equatorial region. One is the centrifugal forces going on, and another one, just it's the laws of physics, when you're getting a lot of particles all spinning down together under the influence of gravity and rotating, they're all colliding and they all adopt the average velocity that's going on, and that happens to be in a nice equatorial plane. So you get this disk that starts forming as the star starts forming. It's called all sorts of names, a circumstellar disk, also a protoplanetary disk, but needless to say, this is the planets start forming in this. So we often call it a protoplanetary disk. And you can start to see this disk forming, the planets form from there, and that's why the planets are all in a straight line or in the same plane. How about that dichotomy of sizes? Why did we have 4 small inner rocky planets and then 4 large ice and gas planets? And that all comes down because of 2 things. One, the universal abundance of elements. We're going to talk about each of these. And the second thing is we're going to talk about that protoplanetary has a disk. Protoplanetary disk has a temperature gradient. It's those 2 factors. So first of all, let's talk about the universal abundance of elements. And whoa, this diagram, and look, you just don't have to look at this diagram, glance at it too much to see the main message here. 98% of the universe is hydrogen and helium, material that goes to make up the gas. 98%. So there's extreme amounts of hydrogen and helium to make gas. The materials that go up to make the ices, which is the oxygen for your water ice, your carbon for your methane, and your nitrogen to combine with hydrogen. So your oxygen plus hydrogen make water, H2O. Carbon plus hydrogen goes to make methane, and nitrogen forms with hydrogen to make ammonia. And that goes to make these ices here. And there's a smaller amount, roughly about 2% of that. Then there's even tiny amounts of the materials that go to make up for metals and rocks, which is things like your magnesium, your silicon, and your iron, etc. So that's probably, I won't even go back there for a while. So that's really an important theme, the universal abundance of an element. So the stuff that goes to make up gas is just oodles and oodles, unlimited supplies of almost. There's much less that goes up to make ice, but that's still a lot more that stuff, materials that go to make metals and rocks. That's a really, really important idea. So the other one is the protoplanetary disk temperature gradient. So as our disk is forming here, as if things are rotating faster and faster and faster, it starts heating up in there, and all the material that we've just seen is in there in that disk starts vaporizing. It gets so hot. So your rocks, your metals, all of your carbon, your oxygen, your nitrogen all starts vaporizing. Then, like all things, it starts to cool down. And when it cools down, there's a certain point when it gets to be a temperature gradient exists, where roughly you've got about 2,000 degrees Kelvin here, and it cools right down, right out to the outer areas, which are a lot cooler, at about 50 degrees Kelvin. So that temperature gradient forms. And of course, with temperature gradient, different materials, well, all your materials eventually, as things cool down, are going to want, that are vaporized, are going to want to condense back into their solid state. And different materials condense back to solid again at different temperatures. Your metals and your rocks are quite happy to condense back to a solid, and degree, you're talking sort of roughly about 1600 degrees Kelvin, they will start condensing out, metal more than rocks. But as you go out and you get down here to about 300 or so Kelvin, and your water ice starts to, the water vapor starts condensing into ice, you get further and further out, and eventually your methane and your ammonia that's been vaporized starts to condense into ice. So different materials have different temperatures of condensation, which, because you've got the temperature gradient, different materials condense back to solids at different locations in that protoplanetary disk. Your metals and your rocks, they're quite happy from all the way out here, they have condensed. The water ice, no, it's still too hot in here, but from here out, they've all condensed back into solid state, and your methane, your ammonia from here. So the condensation sequence end result, let's have a look at that, is that here's your star, here's your protoplanetary disk, and your metals and your rocks have formed into solids from the inner part of the disk right through to the outer parts. But remember, these elements are far less abundant. Meanwhile, your ices, from about sort of, just an arbitrary point, from about halfway out, say, they start condensing through. The temperature's cool enough, but it's too hot for them in there. And the point of this diagram here, the blocks here, is to illustrate the point that there's much more ices than there is rocks and metals. Then, of course, right throughout that whole area that remains as a vapor or a gas, hydrogen and helium remains right throughout the whole region, which makes up 98%. So here is just an artist's impression of the protoplanetary disk. You've got your star and the protostar forming here. So this inner part of the disk, it's mainly metals and rocks that have condensed to solid. And you've got metals, rocks, and ice the whole way out through here. And notice you can almost sort of, I think they've put in there on purpose, it's like a temperature gradient going on. It's glowing here, less and less, and less, gets cooler as you go out. So you're getting the gist of what's going on here with this temperature gradient. So you've had vaporization, you've had condensation process of different materials at different areas throughout the temperature gradient. The next stage that starts happening is accretion. And accretion has got, the main thing is, there's two things that start. First of all, electric static charges. You've got loads of particles in there. They start coming together, sticking together, dust and ice grains, and they start forming into chunks and get larger and larger. And it's electrostatic forces that really is the main process that brings them together up to a diameter of about 100 kilometres. And they're called planetesimals at that stage. The next process of accretion is called gravitational attraction. And that's where gravity is the prime driver of it all, then holds that material together, but also attracts further collisions. There's you've got something yay big, you see something sitting over there, just gravity will pull them in together, and that they grow through that process into protoplanets about the size of the moon. So, at this stage, let's stop and see what we've got. The result of accretion gives you 8 small protoplanets. There's 4 inner rocky ones, but also you've got 4 further out there. They've all got their, remember, the condensation of metals and rocks is throughout the whole area. So that goes right through these 4 big ones here. I just couldn't fit them on the screen, but there's 4 like this that you've got the same rocky metal cores as you've got in the inner part. But this time you've got the outside, say half, you've got ice. And there's much, much more ice than there is of the materials that go to make up the rocks and the metals. So you've got something like this. Once again, this is not the scale, but I've just made these diagrams so to get the principles, make it very clear. And they're roughly about 4 times this. These are obviously about roughly sort of 1 times Earth, roughly the same size. And this whole region here is about 4 Earth masses now. And it's made up of metal, rock, and ice. So what happens is that continues to build up and up and up, and more ice gets up, until it reaches a point of about 10 Earth masses. And at that stage, it's reached a critical mass whereby it can start accumulating all the hydrogen and helium that's around there. And of course, what do we know about hydrogen and helium? 98% of that disk is hydrogen and helium, so there's just oodles, there's no shortage of it. So at 10 Earth masses, you can start to build up all the hydrogen and the helium gas around that metal, iron, and rock core, then all your ices around that, and then all your gas, and there's 4 of those. So you can see what you've got here. You've got 4 inner rocky dense planets, and you've got 4 of these here with rocky metal cores, a lot of ice around them, and then once they've reached that critical mass, they can start piling on all the hydrogen and helium gas, and there's no shortage of that stuff. So remember that diagram, that's what we've got, that's what we started off with after we listed all our planets. And this is an image, you can see this process occurring. This is the from ALMA, the Atacama Large Submillimeter Array, at sort of high resolution infrared views of a young planet, that's a star rather, that's forming with this protoplanetary disk. You can almost sort of make out the temperature gradient going on, but all these dark tracks through here are thought to be probably where planets are starting to form, starting to accumulate all the material and forming planets. So it's quite cool they can actually see it. I'm not brave enough to reach my water over there. So that's the planets, how they got in the same orbital plane. That's how they got to that dichotomy of sizes. So how about the small bodies?
Just a question
Yes.
before we move on. And
Yes.
That was about the migration, the model of the migration of Jupiter. I've read some you maybe going to go on.
We're going to come to that.
I'll shut up then.
Yes, so that was the principle of why you got the dichotomy of planets. Yeah. We'll come short, but that's a good question, yeah. The gentleman's raised the issue of planetary migration, absolutely. So the small bodies, the group, so first of all, you've got your asteroid belt. So why did that big belt of rubble, here it is here, occur between the orbits of Jupiter and Mars? The general thoughts is that Jupiter, you've got your largest planet in the solar system by far, and it's sitting right there. It's huge gravitational influence and tidal disruptions of a wide berth right around it, and there was just too much gravitational disruption for a planet to form. Otherwise, possibly there could have been a planet there, but just the gravitational influence from Jupiter was too much for that to happen. Then you've got Jupiter's, the Trojans and the Kuiper Belt and the Oort cloud. How did those small objects get there? And this is where your whole thing of planetary migration comes into it. So in 2005, group of planetary... Grab your water. Could sit there now. It's become a bit of a joke, really, hasn't it? Yeah, so we won't get too stressed about it. So in Nice, in the south of France, down by the Côte d'Azur, and a group of planetary scientists got together and with their computer models and started crunching numbers to work out, trying modelling what happened with the solar system. Did it always look like this? How do they explain these loose bodies, these small bodies in these certain positions? And they concluded they probably got flung there through planetary migration. And the general idea, I think the next slide, yeah, here it is here. So the early configuration, they thought here's astronomical units across here, and probably they thought it was initially Jupiter. So you got your inner planets and your sun here, but just for your outer planets, there was Jupiter orbiting, and then there was Saturn, and then you'll see in the green there was there's blue on the inside there. There was Neptune. Neptune was next, and then there was Uranus. And so Uranus's orbit was the most outer planet at the time, and that came down to about 15 astronomical units. It was much smaller, compact and close together, those major planets, those big gas giants and ice giants. They were smaller orbits, a lot more tightly packed in together. and Neptune was inside the orbit of Uranus's orbit. Outside the orbit of Uranus, they had this huge, big area of rubble, small objects, that just there wasn't enough of them to form into a planet, so they remained as rubble out there. The disk tends to be sort of a lot thicker and often thins out after a certain point, so this is just related to our solar system. Then Jupiter and Saturn started gravitationally influencing one another with a 2-to-1 resonance. In other words, they were trying to achieve, between the two of them, the gravitational influence. Nature was trying to play it such that they could be nice and stable orbits, whereby Jupiter would do 2 circuits of the Sun for every one of Saturn, 2-to-1 resonance, they call that. So they were busy shuffling between themselves, and in the process, that threw out Jupiter and Neptune. That threw out Uranus and Neptune. They just really got disturbed by what was going on with Saturn and Jupiter being those 2 biggest planets, whereby they started moving outwards. In particular, Neptune went out beyond Uranus, so they swapped places, and Neptune just went out there and ploughed straight into that big disc-shaped area of rubble, and that just sent the rubble flying in all directions. A lot of it went into the inner solar system, and that was responsible for what they call the late heavy bombardment phase, whereby sort of the moon is popped and Mercury's popped to bilio, and all those, obviously a number of billion years ago, that the inner solar system was just bombarded like bilio with lots of asteroid small objects just really going to town, hammer and tongs at the surface of the planets. Wouldn't have been a nice place to be, it would have been a very violent place. They called that the late heavy bombardment phase. Obviously the first one, of course, referring to when the solar system was first forming. And a lot of them also got flung then and found themselves in Jupiter's L4 and L5 Lagrange points to become Trojan asteroids, but also the rest of them got scattered outwards into the Kuiper Belt objects in that Kuiper Belt, and also into the Oort cloud, that spherical Oort cloud, they become Oort cloud objects. So that's the general consensus there, that their models suggested happened early on in the solar system formation. And that explains the comets and the asteroids, where they sit, or sort of, I should say, the Kuiper Belt objects and the Oort cloud objects, because of course they then become those nomadic comets. So what triggers something to become a comet? And the objects in the Kuiper Belt, KBOs, Kuiper Belt objects, they can get quite happily disturbed, because right next door to them, of course, what have you got? You've got 4 outer giants, gas and ice giants, sitting right beside them there that are moving around, and it doesn't take too much for a gravitational disturbance there, and a Kuiper Belt object will start heading in towards the inner solar system to create a short period comet. And remember, these are all rocky and icy, with these ones out here. Or for the Oort cloud, all it would take is some sort of nearby event, whether it be a supernova explosion, or whether it be an Oort cloud instability, or whether it be a star, something passing nearby the Oort cloud. It's all it would take, and that would easily disrupt some of those objects out in the Oort cloud and sends them in to long period comets. Yeah?
Just a question, do comets originate from asteroid belt as well? Or
The comets tend to be more rock and ice, so they're from further out. The asteroids do, but yeah, they get thrown out and they head towards us, but they're labelled as asteroids because they're just purely rocky objects, so they call them asteroids. Now, of course, here's a good one. You might get a comet heading inland that's rock and ice. After a few laps near the sun and all its ice has sublimed off and all melted away, and you're left with a rock. So sometimes you see, oh, look at that rocky object heading our way. It could have been an asteroid, but equally could have been a burnt-out comet that's lost all its ice too. But the asteroids, they just call them as asteroids, or near-Earth objects and stuff, as they head in close enough to us as well. But they remain as asteroids, versus comets tend to have that icy thing about them, hence with their big tails and so on. Okay, so summary, the main points of the talk. The Sun, it's almost 99.9% of the solar system mass. Everything is a consequence of the sun's formation. There are 8 planets defined by 3 criteria. The protoplanetary disk from which the planets that forms as part of the star formation. It explains the common orbital plane, and it is the combination of the relevant abundance of elements in the universe and that temperature gradient in that protoplanetary disk as it's cooling down is the reason for that planetary dichotomy, why you get 4 small rocky planets and then you get your big icy and gas ones further out. So it's all about the sun and making the star. And your main take-home messages, it's all about the star, or in our case, the sun. Sun is 99.9% of the solar system mass. Planets are a consequence of star formation, much like crumbs baking a cake. Have you ever tried baking a cake without spilling crumbs on the kitchen bench? It's all about baking the cake and the crumbs left over. It's all about making the star or the sun, and the planets are just crumbs left over on the kitchen bench. Pluto is not a planet. Never was. Okay, so that's pretty much it. So I hope you've enjoyed a modern perspective of the solar system, what's there and why. Thank you. Taken a few questions. Any further questions on that?
Do you think your Pluto cats are throwing those things in from the outer solar system at us?
Possibly. Wouldn't put it past them.
No, a serious question though. How close in was Jupiter? Because did I read or misread something about Mars being a smaller planet because Jupiter has either perturbed the formation materials when it was earlier in, so there wasn't as much there put as a accrete as you might expect on the basis of its position?
I think there was some interaction. That sort of, they don't talk about that a lot. Grant, are you aware of? No, I have vaguely read in the distance there was something going on between, but it wasn't significant. And they certainly don't bring it up when you start reading up about the Nice model. There's no major talk of it.
Because I was wondering before Jupiter migrated whether it was so close in that it's the accumulation of the gases and the ices came at a much later stage in the development.
Just have a close at that slide. Because that's got your astronomical units there for the Nice model. There it is. Don't know how good your eyes are, but so there's just, because I was going through it this afternoon. There's your 15, and they've put Jupiter in green there. So Jupiter now is about 5 astronomical units, isn't it?
It's stable, I think.
Sorry.
It's always been about that.
Yeah. So look. So there's 5 there, and you go up, and it is. Yeah.
I agree with the article because I read it myself a few years ago. It talked about how Jupiter was a lot closer to the Sun, and it was the migration of Jupiter that caused issues with Mars collecting a lot more than it should have.
Cleared a lot of the orbit
Right.
already.
And it comes in an article based on that's how planet X was created. Okay, because Jupiter forced X out towards the orbit.
Which probably runs with their basic sweeping comment that it's the gravitational influence of Jupiter that is responsible for all the rubble in the asteroid belt without forming into a planet or stacking on top of Mars.
I'm just wondering whether it may not have been a gas giant at that stage. It may have been, had a core, but and then later on when it's migrating out, it's able to accumulate.
Yeah, I think that the clock's ticking on that in terms of what I mean by that is that when does a planet stop growing for all your gas and stuff? And it's got to get it done over very quickly before the stellar winds kick in and blow it all away. Because here's actually, when I do slides, I do takeouts and stuff because I get a whole stack of together and then I don't throw some slides out. I think in case there's a question that's asked, and there's one here that outtakes. People often ask this one, Jupiter and Saturn are greater than Uranus and Neptune. How come? It's because the density of the material was dense, and we talked about that briefly. The density of the disk tends to taper out as it goes out. So the density of the material was a lot higher. But also, so that means the innermost of those large planets, Saturn and Jupiter, get a head start to get up to that critical mass. And they reach the critical mass sooner than the gas kicks in, and then it's almost like the whole process just gets switched off as the stellar winds kick in. And did I put a slide in with that? The T Tauri phase, that's protostars or pre-main sequence stars up to 2 solar masses, or T-Tauri stars, where the sun's fierce solar wind would have halted any further gas collection, blows it away. So that happens all pretty early on in the piece. Yep, so the collection stops for all planets at the same time, and it just happened so that left Jupiter and Saturn got a head start because they were the disk was thicker where they were. So that probably goes away towards answering. But I think we're delving now, our conversation's delving into a lot of hypotheses and modelling and yeah. So, but it's interesting. It's a good discussion. Yeah.
Just to add on to the NICE model, is that considered like universal or like more only applicable to our solar system? Because obviously they're like exoplanets, like Jupiter-sized exoplanet really close to the other stars.
I think the nuts and bolts of the detail of the NICE model is pertaining to our solar system. The concept, though, of migration is well known. Like you see these hot Jupiters. How do they get there? Migration. So I think migration does occur. Really, the question to be asking ourselves, why wasn't there more migration in our solar system? Why don't we have a hot Jupiter? We, sort of our early days when we first getting to grips with our solar system, we thought that this was the model solar system, and everything else, oh, that's a bit crazy, that's a bit crazy. It's actually turning out that we're the crazy ones. That we are the abnormal ones. That's, I think the door needs shutting, yeah. Yeah, it's related to the doors. So, so it seems to be that's more likely to get migration, so why didn't we migrate more? And so we may not be here if it wasn't for the little migration we had, Yeah, Robert.
The question is around, we talked earlier that Jupiter is made up mainly of hydrogen and helium.
Yes.
And then you also said that the atmosphere is mainly hydrogen and helium.
Yes.
What makes the difference between the atmosphere and the rest of the planet if they're both hydrogen and helium?
Oh, in terms of the stripes, the bands and all that sort of stuff, you mean?
Oh, I thought you said Jupiter was hydrogen and helium.
Yes, predominantly, yes.
And then it's got a thin atmosphere.
Yes, of hydrogen and helium, yes. Predominantly hydrogen and helium.
So what's the difference between the planet and the atmosphere?
Oh, sure. Well, how do you call an atmosphere? I think it's to a certain density, and I think there probably are planetary criteria where it would get to a certain density and the planetary scientists say, we're going to start calling this now the planet and not the atmosphere. I don't know off the top of my head, but I'm sure there'd be some criteria for that. Yeah, but there is no well-defined solid surface you can walk on, but it does get to a point where it's pretty dense and solid, but it's a pretty fuzzy line over probably, I would imagine, hundreds of kilometres, I would have thought. Yeah, it's a blurred line. And when does something become, we're going to start calling that an atmosphere? I think probably is an arbitrary definition somewhere, I would have thought. Yeah, but it's a continuum.
What do you think the big core is?
Yeah, so the core of Jupiter is interesting. It's thought to be hypothesized to be the conditions where it's probably metallic hydrogen. Yeah, so you're getting, but it's just one big continuum. And the other thing is because, Jupiter's got a really strong magnetic field. And you think, what gives it that? It's a combination of things. The big one is, it's metallic hydrogen core. It's spinning once every 10 hours. That causes this big strong magnetic field. Yeah. So it's just a big continuum. How dense does it get and how big's the atmosphere? It depends on the whole mass of the planet. The higher the mass of the planet, I would have thought the smaller the atmosphere would be because of the compression down. It's more dense. And that's one of the reasons why Saturn differs a little bit. Saturn actually has got a slightly deeper atmosphere than Jupiter. It's not quite as massive, so you haven't got the downward force so much, and that's why you just don't have quite you have slightly higher atmosphere, and that explains a few observations you make between the two. Yeah.
So Chris, in one of the early slides, you had a diagram showing the orbit of Pluto.
Yes.
And it's
tilted up at an angle, I think 17 degrees, if I remember off the top of my head.
Yeah. It's a different angle, but also it was simply showing as an elliptical.
Elliptical, yes.
Right?
Yes.
And what's the suggestion that's brought about that difference?
Yeah, so you see all the planets are all nicely all lined up, and they've got reasonably circular orbits and all in the same plane. And yeah, the Pluto, it's tilted up about 17 degrees, and it's more highly elliptical. It crosses in front of the orbit of Neptune at times. Hello, what sort of planet does that to its neighbouring planet? Jeepers, that's a bit unfriendly, isn't it? So that alarm bell should have been going off there, but particularly it was cutting in front, it's tilted up. So that's highly suggestive it did not form with the rest of the planets. It's probably been biffed there with that migration. You know, it's sort of when Neptune ploughed through that earlier bunch of small bodies, they all got shoveled out and Pluto was in the mix. So it didn't form nice and orderly fashion. It's not a planet, yeah. Steve, are there any online things? No, that's all good. I think they've all got their ears all blasted from our alarm.
Just a question about the Oort cloud. You said it was hypothetical. I didn't know that. I thought they'd found some.
I'm unaware of it. Well, the evidence, I think, is sort of mathematical, is because of where of these long, when I say hypothesis, I don't think they've actually visualised, we can see an Oort cloud object because they're relatively small and they're so far away at a light year, they haven't seen them. But the mathematical calculations are very strong evidence that it is there because of those long period comets that are coming. They've got to be coming from somewhere and they all appear to be. And it would tie in. The other thing is when you run your computer models, your simulations, when you get that Neptune ploughing out and stuff flies out, yes, some of it does form into a nice torus donut around from the Kuiper belt, but a lot also gets flung out in all directions.
So I was thinking that comet Kohoutek was meant to have a period of 30,000 years or something. So would that be probably an Oort cloud object, not a Kuiper belt object?
Yeah, because remember Oort cloud is 55,000 astronomical units or light year out there. That's a long distance. Yeah. So yes, yeah. Anything greater than about 200 years is thought to be from the Oort cloud. Yeah.
I'm just curious about that really early slide you had with that model of the solar system. Do you know when and where it came from?
Oh, right. Oh, yeah.
It showed this like fifth planet, like in between Mars and Jupiter.
Oh, right. Yeah. Okay. Yeah. The very first one, the model. Yeah. Look, I just found that off the end. I just typed in old model, outdated model, 1970s solar system, and that came up. And I thought, God, I remember seeing things like that.
And just like between Mars and Jupiter, it's like a planet instead of the.
Oh, I think that was just their way because it was a model. That's the only way they could represent an asteroid belt. They couldn't have a belt because it was just all bits of, on metal poles going out. And it was more symbolic. I'm sure when they made it, they knew what they meant, but it's all they could do was put a little point. You've got a very observant there.
I mean, basically the planets up to Saturn were like known like in the antique times, right? So no one would make a model like this. Later on, pretending there would be a planet.
Yeah. I think that was my point. Yeah. This is the sort of models that got thrown to us at school in the 1970s. That was the model we were given. Sun's in the middle. What's sun? A star. Oh, a bit more. No, that's all you need to know. There's 8 planets out there. Yeah, the different sizes. That's enough. There's some rubble there. That's enough. But suddenly now, with the next generation of telescopes and space telescopes, computers and stuff, we've got a far better understanding, and that is my thrust of my talk here. It's a modern perspective of the solar system. We got a better idea what's there, but also we know why things are where they are and behave as they do.
The thing that model does for young people too
yes.
is it doesn't give the sense of scale. When you think that Saturn is as far away from Jupiter as Jupiter is from the Sun, and basically space is empty.
Yeah, exactly. And I think that's a difficult way. I think with astronomy it's hard, when you're in physical models for kids at school, it's really hard to put in, and that's kids can't...
The ball and the pea.
Yeah, wonderful.
Yeah.
The pea on a rugby field.
But yeah, I think that's the best you can do with kids. You're not trying to teach, I suppose, logarithmic scales and distances. You're just trying to impart the principles that there is a central sun and you've got these planets go out from there and names of the planets, and they sort of get that stuff later on. But
we have all these pictures of like spaceships navigating through the asteroid belt. Well, everything that's been fired through the asteroid, nothing's struck anything yet. They're probably thousands of kilometres apart, each of them.
Yeah, like in the movies, isn't it? They're dodging asteroids, driving like that. But in actual fact, that you'd probably have it on cruise control, watching a movie up the back of the spacecraft while you're doing it. Yeah, eating some KFC or something. Only in New Zealand, yeah. But yeah, let's go back there. But there was, by the way, So that's Boston, that's Maya, and that's Stella. Boston's my buddy for when I do my observing out. I go out to this little paddock across the road, and he's always out there. He hears me put the telescope, and he runs, don't forget about me, and out he comes. So when I got Brian Green was here last week, so I got him to sign my book to Chris and Boston. I said, Boston's my observing buddy. But yeah, that model, But that was quite cool, isn't it? The Venera, pretty much the images that you see off the surface of Venus, and it was just the craft only survive.
Were these original colour photos, or were they taken in black and white?
I think they might have. I have seen black and white pictures. They might have been slightly colorized. I'm unsure. Good question. Yeah, good question. I did see black and white ones there, but I just thought they were. I thought, yeah, I'll throw them there. Yeah.
Didn't they have no electronics on the lander? It was just all analog.
I wouldn't be surprised if the electronic wouldn't have lasted long, but even the probes coming down, they did not last long. Yeah.
It must be able to transmit, so there's something very digital about that. Oh, maybe not digital, analog signal.
Here we are. Yeah, so we'll come back to that
Must
model.
have sent a signal back to the orbiter or something.
Yeah. Yeah, we didn't exactly send the film back.
No, no.
There's all our Y. And here you go. Here's your famous model. Yep. And I think that's the asteroid, that little blue one then. They've dropped it down. And I think that's just what they meant there, but being very observant here. Any other questions or queries? So we'll get home. Yes, what one more?
So the formation process in the Kuiper belt is quite similar to the planets, but more chaotic and no dominance. So the formation process in the Oort belt is completely different. That's really just a condensation sort of.
In the Oort cloud?
Yeah.
Yeah, I think all the material formed, it was all vapor, it was all part of that disk, protoplanetary disk. And you had less and less material to tapered out as it went out. And all that material got vaporized, condensed back again, and you would have had your ices and rocks out there as well. It just wasn't enough material to form to a planet. So it just remained as rubble, and then it got biffed out there when Neptune came ploughing through. It got biffed out there, so it didn't form in the Oort cloud.
Okay, so the Oort cloud is spherical or planar?
It's thought to be spherical with the mathematics of where comets and that their orbital properties.
But the thinking is that the Oort cloud is a property of Neptune's movement.
Yeah, Neptune ploughed into, you had all these small bodies that weren't enough to form a planet just outside of Uranus. Neptune ploughed into it and just sent it into chaos and scattered these objects that just flew out there.
Kuiper belt, rather than
And Oort as well. So both, that's impression is that they both...
Oort cloud objects were formed in roughly the same region as the Kuiper belt, but pushed out by Neptune.
Yes, scattered out there by the migration of planets.
So out there could be bodies, possibly many, just as big as Pluto.
Well, then you get, the Kuiper belt, they haven't even really fully explored. How far out does that go? There's all this evidence, people say, is there Planet X out there? And all this sort of stuff, like the likes of Mike Brown in California. That's his hobby, is searching out there and they're trying to look for it. And people often say to me, Planet X, does it really exist? And I go, there's weak circumstantial evidence for it. No one really knows yes or no, but the evidence is pretty weak and it's pretty circumstantial. I heard Neil deGrasse Tyson say once too, most of the gravity in the solar system has been accounted for.
But there's half a dozen objects, at least, of the size of Pluto.
Yes, correct. Yep.
And an unknown number of such objects.
Sure. Yep. Oh, it's that whole Kuiper belt and all beyond that outer solar system is a whole area yet to be explored. Yeah. So, we don't know what other things could be left because you're getting so far out, it's hard to see them, they're so small. And that's why New Horizon now is heading out that direction too, and there's sort of hopefully will add some value, But, your point being taken is that,
Do you expect to see massive objects in the Oort cloud? No. Because the amount of energy needed to throw them out that far, because you're talking like 50,000 astronomical units or 100,000 astronomical units.
The energy is proportional, isn't it? The energy would come from Neptune and the interaction with it.
That's right, but if you've got a heavy body interacting with Neptune's not going to throw it out as far as it's going to throw a cometary body. So basically, most of the Oort cloud is cometary body. So you've got this population of comets that are coming in from very high
Would it make that
eccentricity.
much- I mean, would it make that much difference? I mean, Neptune is hundreds of times, thousands of times bigger than these objects.
Yeah.
So I'm not.
Yeah, so it's doing the throwing.
Right,
I'm
but
saying
I'm
what
not
gets
thinking-
thrown
I'm not
out,
thinking the
but you
strength
won't,
of
you won't
throwing.
have planetary mass bodies out in the Oort cloud because
Right, but
there isn't
wouldn't-
enough.
Wouldn't the energy be proportional based? I mean, it's not like these bodies are similar in size to Neptune, so you're getting a different. They're going to be flowing just as hard by Neptune as a small body.
But they're all small
Yeah,
bodies
but-
because there wasn't enough material to form a big body out further out in the disk.
Yeah, right, but they're forming
You'll throw a
Pluto-sized
cricket
objects,
ball a
right?
lot further away than you'll throw a big heavy ball. So I mean, basically, it takes a lot more energy, gravitational energy, to throw a heavy body out into the Oort cloud.
Right, but what I'm saying is that Neptune's got more than enough gravitational energy because it's so much bigger than these bodies.
Yeah, but okay, so but most of what it's throwing out is relatively small. I mean, we know.
Oh, yeah, but no, I
Let
agree
me
with
finish.
that.
There's a whole bunch of sort of planetoid bodies
Yep.
that are now being discovered just because we've got better cameras that are out to, sort of maybe 5 or 6 times or more further than Pluto. I mean, maybe dozens of times, but nothing like the Oort cloud, which is like a light year. So I mean, there's a huge difference in the distance. So you cannot throw a heavy body. There's nothing in the solar system apart from Jupiter or the Sun that could throw a massive object out into the Oort cloud. So basically, the Oort cloud has got huge numbers of objects in it, but none of them are very massive. And the planet, the subplanet ones, like heavy asteroids that are in the, they're all in close. So they're nothing like the 50,000 astronomical units that most of these cometary bodies are. And a whole lot of them got shot out of the solar system altogether. So the Oort cloud's population of comets is only a small fraction of what got thrown out. Most of them got thrown right out and never came back. So so that, I mean, so there's no reason to expect there's going to be a massive body out in the Oort cloud, for example,
But you'd expect more dwarf planets in the Kuiper belt, which is closer.
Yeah.
Yes.
Yeah.
A lot closer. Yeah.
Because it hasn't been moved as much.
Because
Well, no,
they're more
because
massive.
that's the furthest that they could get thrown out with the mass of the objects you've got to play with. So, I mean, it's not the Sun that's doing the throwing out, it's objects, like the planets, like Jupiter in particular, and Saturn, that actually interaction with those heavy ones are the ones that threw out, so all the light bodies, those planets can either eject them from the solar system altogether, which a large number must have, but some of them didn't quite make it out and still just got held by the Sun, and so they're out to like a 50,000.
So I have a misunderstanding perhaps of Newton's laws of motion. That's that if you've got a body and you've got an object that's thousands of times bigger, the acceleration that that other body experiences is going to be, almost the same. So it's a matter of how close it comes and in what trajectory. Not unless its mass is really similar to the other body, it's going to get accelerated just as much
As what?
as a body that's 1 million times smaller, which is like a small asteroid. They're both going to experience pretty much the same accelerations because of how gravity works. Now, the chance of it happening is much lower because density of these other objects is much lower, but if they do encounter Neptune in the same sort of orbit, they're going to get thrown out just as much.
Related that, I was thinking that if Neptune moved out on the same plane and the Oort cloud is spherical, I can't imagine it would be an even perturbation to put a spherical
But
mass
it's not,
right around.
it's probably not spherical.
Yeah,
All
yeah.
the modelling shows that it's got sort of structure to it that's non-spherical.
It's got inner and outer zones, it's got little bridges and stuff. There is quite some structure to the Oort cloud, as theorised anyway through calculations,
Structure relative to the plane, the internal plane of the solar system, which is defined by the Sun and
makes
Jupiter,
sense.
basically.
Yeah. Interesting.
Interesting. All right, guys. Well, thank you. I think we'll wind it up there, and hope you have a safe journey home. And thank you, and hopefully we won't have the alarm next time. Thanks, guys. Thank you.
Thanks, Chris.
Thank you.